Hope all of us are doing great. My name is Ernest, and this is Ernest Sciences and Mathematics TV channel. Today we're going to look at the concept of entropy of a monoatomic ideal gas, and of course we're going to look at various aspects of the concept of partition function, which we have derived for other thermodynamic variables. Now in this case, I'm going to rely on our previous discussion that we had on the basic concept of entropy, and of course I've mentioned that basically we can have a relationship between these different thermodynamic variables in terms of a simple equation. Now in this case, I've given the concept of entropy as the difference between internal energy and the product of absolute temperature and entropy. Therefore, from this one, we are going to basically this holds energy is equivalent, free energy is equivalent to internal energy minus the product of absolute temperature and entropy. And this gave us a basis for finding the representation for the concept of entropy, where we say that, and therefore entropy from this one can be given as a subject, where we're going to have it given as the difference between internal energy and the Mole's energy all over the temperature given as such. Now from our various representations, I decided that basically we can use the concept from internal energy representation of a partition function and the Mole's free energy in order to find this specific aspect of the numerator which I've given in this particular case. Now from our discussion, I've given that basically the internal energy, so I'm going to put a link of this in the description box. We can have the representation of internal energy as a product of Kp, the square of T, and the partial derivative of the natural logarithm with respect to temperature, and this is going to be given in terms of that one under constant volume given as that. So this was a representation for the internal energy of that specific system under consideration. And of course, we have given also the similar representation for the change in Helmholtz free energy in terms of a partition function, which gave us a negative kBt, and then we had this one as the natural log of Q given as such. And therefore, these two specific aspects on the right are going to give us the difference in energy between these specific two for the internal and the Helmholtz energy. And of course, that's going to assist us have a general representation for this specific aspect of entropy. And we came up with a general equation representing this aspect of entropy. And therefore, that one gave us the equation of K, Pt, and the partial derivative of the natural logarithm of Q with respect to temperature and a constant volume. And this one, of course, was together with Kp natural logarithm of Q as such. And this was our general representation of the concept of entropy from our previous discussion. And this is going to lay a basis for us in describing the entropy of a monoatomic ideal gas in terms of this partition function. Now we had listed a few characteristics of this monoatomic ideal gas. And we said that basically we're going to rely on the concept of translational partition function and trying to neglect other variables, since we had mentioned that for us in describing this specific aspect of a monoatomic gas, the translational function aspect that we're going to consider in this case is a translational partition function. And therefore from my previous statement, and therefore we're going to only consider this one by doing a substitution in this specific formula. Now from different discussions, we had some representation from this, which is going to take consideration of temperature. And basically then therefore I'm going to give a fraction of this one and this one from our previous derivations of the aspect of a translational partition function of a monoatomic gas in that aspect. And therefore those are going to form substitution for the first part and the second part of this specific equation. Now, from our previous discussion on the concept of internal energy of an ideal, a monoatomic ideal gas, we're going to consider this first specific aspect of the equation from that particular discussion, whereby we had mentioned that we can have this total partition function for a monoatomic ideal gas consisting of n particles, and of course it's going to be given in terms of an atomic translation partition function, whereby we said that for indistinguishable particles, we're going to have this one given in terms of Q, n, and n factorial given as such. And this, of course, gives us a version of the equation in consideration of the de Broglie's wavelength in terms of n phi to power n given as such. And this was basically our representation of this specific partition function. And of course, we're going to have this one then therefore written in terms of U, whereby we're going to have, as I said, from this specific equation, the internal energy then therefore can be given in this specific form. And we're going to consider, as we said, that aspect of this specific case, which is going to rely basically on temperature. Therefore, the version of this part of the equation can be given in consideration of that specific aspect of the partition function in terms of internal energy, whereby we can have this, as we said, internal energy given in terms of kBT, and this is the square of this temperature. And therefore, for the second section, as I said, we're going to rely on those specific aspects of Q, which are going to rely on temperature. And from this case, of course, I had mentioned that the de Broglie's wavelength is going to be a factor that's, of course, basically a factor of our interest, since it's the one that is going to rely on this temperature. Therefore, this specific equation then therefore is going to transition in a way that we're going to substitute or do a substitution of this specific numerator for the derivative, the partial derivative, and we're going to have this one given in terms of the de Broglie's wavelength, and it's going to be over n given as such. And then we're going to have this one all over the partial derivative with respect to temperature, and this is going to be under a constant volume as I mentioned. So therefore, this specific consideration for the factors of aspect that depend on temperature is going to be considered, and therefore we are going to have this specific substitution in this aspect of the partition function given as such. And therefore we are going to use the laws of a logarithm for this specific equation, and therefore to be given in terms of that aspect of temperature. And of course, because of our space, I'm not going to go further into details, but I'm going to put a link over this specific video on the concept of internal energy of a monoatomic gas, which is going to assist us derive a specific aspect of this first equation, which I'm trying to give this specific point in terms of a summary. So therefore, we're going to have this particular internal energy given in terms of that one, and the partial derivatives of that specific natural log of t 3n over 2 all over the partial derivative with respect to t given as such, and this under constant volume. So therefore, from this specific representation, then therefore the representation of entropy from this particular part is going to be given in terms of this aspect of temperature. And therefore, for the next one, we're going to consider the representation according to the de Broglie's formula, which gave us, of course, the aspect of the wavelength. And I'm going to use our previous discussion we had on the concept of translation, partition function, especially on the concept of approximation. Now, we said that the various aspects of the integral quantum numbers are going to be considered in terms of a continuous variable. And of course, we had done a replacement for this specific aspect of the summation sign together with this. Of course, we had a transition from the summation sign to this specific integral. And that one, of course, I had mentioned that this is going to be of assistance for us in trying to make use of the standard integrals in finding the value of this translation energy. And I had given our translation partition function, and I had given this specific representation whereby we had the translation, the solution to that specific integral of the translation from the summation to the integral, given as m k bt, and this of course was an h, which basically was the de Broglie's wavelength given in an inverted or inverted form. And of course, we had this one given over 2v given as such. Now we have considered volume as for a cubed box. We have said that this is going to represent L raised to power 3, which is a cubic in that particular case. In this case, therefore, we're going to consider the aspect of this translational function in this second aspect of the equation, and it's going to be given in terms of this specific wavelength, which is a representation of the translation partition function using the de Broglie's wavelength given as such. Now, therefore, this is going to be expressed in that specific form, but we're going to consider the aspect of this specific gas, which are mentioned in terms of the distinguishable and indistinguishable, of course, particles equation. we're going to do a substitution for the total partition function in consideration of this specific representation, and therefore this factor of Vn over n factorial are going to be considered in our specific equation for representation of this specific concept of entropy. Therefore, we're going to have a function of this equation given in terms of S is equivalent to kbt, and then we're going to have the natural logarithm over this t3n over 2. And this, of course, I've explained it from this specific aspect of this particular transition function, which is being considered with factors which are, of course, related to temperature and neglecting others. So this, of course, is going to be given in terms of that. And, of course, we're going to give this specific aspect with, of course, the condition of under constant volume. And the second aspect of this, which is kbt, of course, this is going to be kb, and the natural logarithm for this q, of course, I've given a consideration for this. Therefore, it's going to be given in terms of 2 pi mk bt, and then we're going to have over the square of h given as such, and this is going to be 3n over 2, which has a subset, of course, from this specific consideration, then therefore it's going to be given in terms of Vn over n factorial given as such, and this is going to form a representation for the concept of entropy. Perhaps this formula is confined, but this is going to form the first bit of this, and then we're going to see that this second aspect is going to represent this specific function, and that basically is a substitution for the total partition function, as we said, whereby we're going to consider only variables that are, of course, related to temperature in the first case, and of course, so we're going to see that for the second case, we're going to consider this specific aspect of translational energy which I've given, which is, of course, going to be the internal energy of a monoatomic ideal gas being taken into consideration. Now, therefore, we are going to see that in us finding a solution to this specific equation, I'm just going to have it given as an equation, and therefore we're going to see how we can use the various laws of a logarithm in finding its evaluation. But up to this point, I presume that we have understood the procedure, and then next I'm going to show how we can evaluate this using, or simplify this using the various laws of logarithms in order to solve for this aspect, like the factorial we are having in the second part. Now, therefore, from the board, it is going to represent our general expression for the aspect of entropy, as we had mentioned. And of course, we're going to, as I said, try to solve this one as mentioned using a specific set of logarithms or laws from logarithms, especially in trying to look at this specific aspect of the concept of n factorial. Now, for us to achieve this, we're going to use a Stirling approximation. So we're going to use the Stirling approximation in solving this specific equation, which is, of course, going to be applicable for large numbers of particles given in that specific case. So this basically is the natural logarithms over n n factorial is equivalent to n the natural logarithm of n minus n, and this is going to be the approximation which we are going to use in trying to solve this specific equation. Then therefore we're going to do what we call a substitution, and of course evaluate this specific derivative with respect to temperature for that specific of course equation, which is going to be given in terms of the derivative, or rather the partial derivative of T3n over 2 with respect to temperature under constant volume, and see which product we are going to get. Now, for the first aspect, of course, which is this specific part, I'm going to use this one and perhaps try to give an elaboration of what this basically is. And because of space, I'm just going to give it as is, and then I'm going to give an elaboration of what this basically aspect entails. So this is going to be 5 over 2 n kb, and this is going to be n kb, the natural logarithm of this second part, which we're going to give as 2 pi mkbt all over nh. So this is going to be Planck constant to the power of 3, and this all of this is going to be given in terms of so this aspect, this upper numerator is going to be given in terms of 3 over 2, and then we're going to have this one given in terms of v, and that is going to be given as that. So we're going to have this specific version of the equation transformed into this lower part of the equation, and this is in consideration of the fact that we are going to consider Stirling approximation for this number of n factorial for large number of particles, as we said, and this is going to give me a version of the equation given in this specific format. And of course we're going to do a substitution, as I said, for various aspects of the derivative with respect, of course, a derivation with respect to temperature, and do some substitution which are going to assist us to obtain this. Now, from the concept of ideal pressure, or the ideal concept of the consideration of the pressure aspect that we have derived in our previous video, I mentioned that we are going to represent pressure in terms of course, the partition function, whereby for pressure for monoatomic gas, I said that P is given in terms of N kBT 1 over V given as such. So we're going to do a substitution for this specific aspect of pressure, and therefore this is going to give us a version of the equation which we're going to have represented in terms of Sm is equivalent to 5 over 2. So this is going to be representing basically R, and I said that from the Boltzmann's constant and the, of course, universal constant, we have a relationship where R is equivalent to Na or NaKb given as such. So we have NKb given in this specific case, and therefore we're going to substitute this one for R plus R, the natural logarithm of this section, second section of the equation, which is going to be, of course, the space is limited, but I'm trying to trying my best to write it in this form. So we're going to have mkbt all over this one. So we're going to have Na, having done a substitution for pressure, H3P, and then we're going to have this one given as, this is 3 over 2, and then we're going to have RT as part of this specific numerator. So we're going to have this specific equation transit into this lower section of the equation, and of course this section of the equation that I've given under my lower part is going to represent what we refer to as the Sackur-Tetrode Equation, and of course that's going to be representing the molecular translation entropy of an ideal gas, which we're going to see that was basically our topic of our discussion. Now we're going to use this specific equation in some of our of course discussions, and I hope that although it was somehow cumbersome, we're going to look at it step by step and try to interpret on the various aspects that we have discussed. So that is it for now, guys. By God bless you. Catch us in our next video.